His name over there has his view.
But I tell you, if you go out of this room...
It'll come to you. It'll come to you.
But you go 2 blocks outside of this room, there's a lot of people who have no view.
Yeah, and a lot of people have no views.
Yeah, absolutely no view.
But my own view is not all that different than my colleague over here. It's not that I think there's going to be some deterministic theory that's going to underlie quantum mechanics. I think it is going to inform how we think about quantum mechanics very deeply, and it's going to change in an enormously big way the way that we think about quantum mechanics. That I am sure of. Whether it will be the way that, that Raphael and I have proposed over the last couple of weeks, or the way that Hufter has proposed for years, Herman has his ideas, I think that remains to be seen, and it is a work in progress. I think there will be progress on it. I think when we come back here, maybe not next year, but 5 years from now, there will be more knowledge. But it's very clear we're on the cutting edge of, and on the cusp of, I think, a major paradigm shift in the way the world works.
All right, that's great. Now, how are we doing? We're feeling pretty good about holographic principle and projection, right? Right? And we're feeling pretty good about how information is a much more complicated thing than maybe the concepts from our intuition, right? Right? Okay, good. All right, here's a question that's going to put you on the spot. But it relates to your issue of each of you think differently. The physicists are as different as snowflakes. And hopefully they stick around longer than snowflakes. If I were to put a holographic principle T-shirt on each one of you that specified how each one of you represents a particular sense of what's going to happen, what we're going to discover, what aspect that represents your position, what would your T-shirt say? I believe in holographic principle, and it's going to look like blank.
I don't know. I would like have something like I heart HP or something.
Well, that's going to be on the back.
No.
The front is going to have to
Your
be more...
ticket to quantum gravity on the back.
Your
ticket to quantum gravity.
So,
I mean, why do we call it a principle? Like, you know, I think the positive spin, the most positive spin I can try to put on this, and I am being optimistic when I say this, is compare this to the equivalence principle. The equivalence principle is something that Einstein recognized, you know, a huge conspiracy in nature. Why do all objects fall at the same rate? You know, different particles with different charges do not get attracted to each other at the same rate. But with gravity, for some reason, everything gets attracted in exactly the same way. Amazing conspiracy from the point of view of Newtonian theory. You just have to put it in by hand. It doesn't contradict anything, but it's just crazy. It needs an explanation. So he elevates this observation to a universal principle. You have to find a theory that makes this obvious to start with.
So for you...
And that would have to be quantum gravity, because what's involved here is both quantum theory and general relativity. It would have to be a theory that knows about both. So it clearly is a signpost. Maybe we need more signposts to find the right answer.
But for you, holographic principle is a first step towards a theory of quantum gravity that begins to explain what's so frustrating about gravity.
Well, and indeed, what Gerard just said tells us why it's been so hard. You have to explain where this holographic bound on information comes from, while not destroying what we know about locality. The fact that I get to know in this part of the room something independently of there. I get to move particles around independently. It seems like you don't have to know what's over there to do something here. There seems to be a conflict here between holography and the way that physics has worked up until now.
On your T-shirt, Herman, what would it say?
I mentioned the movie The Matrix. Probably some image like these letters, and there's Nemo. What's his name? The guy who he goes and he starts flying with anti-gravity. I think that's pretty good. So let me explain why the Matrix. We talked about sort of things not being able to move faster than the speed of light, and I think the people that came up with the name of the Matrix actually had something pretty good in mind there. Because what is a matrix? It's essentially something that relates something that's here with something that's completely somewhere else. So I think indeed that sort of the future, at least of this development, will be that we start actually with information. So information is going to be our starting point. And space-time is not something that we start with. We forget about what space is and what time. And then somehow the information, by thinking about how much information is, what information is doing, then the space-time will, what we call, be emergent. It will come out of just a bunch of zeros and ones. And here's one idea that I think actually I can put it here just since no one's listening and I can just say what I want.
They're listening, I guarantee you.
So
there's no non-disclosure thing.
So we talked about information, and one of the things, by the way, that information tends to do, again, it gets lost all the time, actually. That's called the second law of thermodynamics. The lost information, we call it entropy. Entropy always increases, chaos increases. And that's a fact that's true in our universe, and it's a fact that's true in other universes as well. So it's a very fundamental fact of how things work. And what's probably also true in other universes is that things indeed fall. If you drop them, they'll go down. And it seems that those two facts are very closely related. The fact that information gets lost all the time, and the fact that things fall. So I think that's...
And lost is different from destroyed.
Lost, when I say lost, indeed, it's going to be the known unknown.
Right.
So it's
Got
the known unknown, the increase in the known unknowns that's responsible for space-time, for curvature of space-time, for gravity, the fact that things fall.
I mean, what you're suggesting is that, when I forget something, instead of just having a kind of a pre-senility moment, I'm actually participating in a grand march of our understanding of the universe.
Right, that's correct.
Yeah.
That's correct.
I'm loving it. I'm glad I came tonight. Gerard, what would be on your T-shirt or sign that would suggest where you fall on, and I guess probably the pre-quantum theory, the proto-quantum theory might be on your T-shirt. That might be the direction that you would be headed.
Yes, I will continue to ask nasty questions and say, well, you can have this fancy, beautiful idea, but remember that there are fundamental principles on which the original idea was based that you're losing out of sight. And so this was why I mentioned causality, the fact of the order of cause and events. That is, to me, a very primary law or rule of nature, that everything that happens here has its origin in the past. That's what we call causality. There's a cause of everything happening in this world. That's how laws of nature are being formulated. If you don't have that, you can, for instance, go backward in time and you have circular situations in time, like you can go and kill your grandfather if you could move back in time. That's clearly nonsense. Then you get circular arguments and you get chaos in the laws of nature themselves. Nature cannot solve its own equations. That cannot be right. We must have the principle of causality. Now, this is somewhat at odds with this holographic principle. I don't say it's entirely at odds, but there's some tension here. And what we want, the whole reason why we are doing this, why we're making this, all these considerations, is that we want to have a better model, a better theory of what happens in the physical world. We want to explain why the particles that we have today behave as we have seen and studied them today. And there are many things you understand and many things you don't understand. We have the standard model of elementary particles is a beautiful rigid scheme of all particles known today, and it is marvelously precisely described by this standard model. But there are mysteries in it which we want to understand and solve as well. We are very ambitious. We've made a marvelous theory of nature. It's not good enough. We still know there are blank spots in this theory that we want to fill in. And this is why we are doing this. We want to find new basic principles to improve our understanding of nature. That's what all of this is about. But the only way to understand to improve our understanding of nature is by asking all sorts of nasty questions. Questions our colleagues rather not ask because they're so confusing. Well, let's ask confusing questions anyway and see if we can come close to answering them. Any question that has an unexpected answer might help us go forward and make an improved theory of the world that we live in. That's what the real reason is for this exercise.
And I love this idea that possibly one way of thinking about causality and the forward march of time is as a information state, as a sort of an understanding of the march of time as a set of information that you know, one event leads to another event. That
it's
sort
a
of thing.
vision that the universe is very much like an information processing machine, just like your laptop or any other computer. I like to view nature as a gigantically big computer that has information going into it, and information comes out processed. The processors, they are the laws of nature. The laws of nature say that something happens, some particular configuration goes in, it's being rearranged, and another combination of data goes out. That's how in physics, traditionally, we consider the process of particles touching and scattering against each other. Two particles come like this, they hit each other, and they go off in the other direction. That's what we call scattering, and a scattering process is an important way of describing the laws of nature. What happens when two particles meet? How do they separate? Do they break each other up? Do new particles form? And so on and so forth. So that's a fundamental way of phrasing laws of nature, and that's what we want to understand.
Can I ask you a question on this? Again, if we talk about pre-quantum mechanics, in quantum mechanics we know that at least one of the foundations of physics, quantum mechanics has thrown it out of the window, because one of the foundations of physics was that if you know what's happening at a certain moment, what the situation is at a certain time, then one step later in time you would know what happens next. But in quantum mechanics you can have two completely identical situations that a snap second later would give you two different outcomes.
That is right.
Is that a principle that you accept, or is your pre-quantum mechanics going to be of the type where you...
It's a principle I accept entirely within the language of quantum mechanics. But my suspicion is, it's only a suspicion, is that quantum mechanics cannot be the entire story. There's something else happening, and you're exactly asking the right question, which is, how come that if two particles reach each other, and in the beginning they were identically the same, and then suddenly they might do either this, or they might do that, or other particles might come out, and all that is described by a matrix, in fact, in the quantum mechanical sense, but nobody knows how to predict which of the possibilities is actually being realized. That, I think, is a weak spot in our present understanding of quantum mechanics. Why is it impossible to predict in advance what will happen? And there are numerous examples of this which are typical for quantum mechanics. And physicists today have learned to ignore the problem, to say, we solve everything, except we cannot always predict exactly what happens. What we can say is that you need all the possibilities to compute what happens after that. So that's a mysterious feature of quantum mechanics.
And you want to embrace the mystery rather than ignore.
Exactly.
A little bit, okay.
They've learned to do that because it is so successful. It works tremendously well in understanding nature. But it cannot, to my taste, it cannot be the entire story. There's something else happening, but at a different level of nature. And my belief is the Planck scale is so much different from the scale of elementary particles that could well be the level at which things are fundamentally different. There you have, if two things scatter, they have only one choice to make, not many, very many. That's the idea of determinism, which people laugh at. When I mention this idea, people just manage to keep their smile away from their faces, but otherwise, you know, as soon as I'm away, I'm sure they're laughing about this idiotic idea of determinism.
Well, we can check some of the comments on the website later.
It's not a crazy idea, but
it's an old idea.
It's an old idea, and it has proven wrong about 1 million times. But always they prove wrong because they're making very conservative assumptions, and I don't believe those assumptions. So I still think there's a way to get around this. But that's very, very difficult. And it's a dispute that's going on for years and years and years, starting all the way back with Einstein and Niels Bohr. All historians of science say Einstein was wrong, Bohr was right. And I believe it's not true.
That's
well, nasty questions fits on a
what
t-shirt.
goes on the t-shirt?
Nasty questions does fit on a t-shirt. That's good. Leonard, yours.
Well, just with respect to what Gerard says, I wouldn't bet against what he says. On the other hand, I just can't see how it will work. But it's those kind of conflicts which get us where we want to go. But my T-shirt, well, if you can't say the Brooklyn Dodgers, I guess I would like it to say the UV-IR connection. Now, the reason I say that is to give me an opportunity to explain something else. Give me 5 more minutes to explain something else, which we will probably all agree about, but which is a very bizarre property of nature, at least if the ideas we're talking about are correct. It's not totally surprising that as you try to get a more and more accurate description of nature, it looks more and more scrambled. To get the best description of nature, you have to account for all the degrees of freedom. And sometimes it's just too much of a good thing. I mean, you know, we know what happens when you try to have too much information. Too much information can lead to a situation where you're just completely confused because you're just flooded with it.
It would be like you mount a camera over the city of New York, you put a light on everybody's head, and over time you specify where they go. It looks great for about 10 minutes, and then
well,
it's mush.
even taking a sharp snapshot at an instant, too much information will flood you. You know, we know the CIA gets so much information that it doesn't know what to do with, and it's just got too much. It's not too surprising. You know, you'd learn much less about a body of water with a surface and so forth if I gave you a description with a table which just gave you the position and the velocity of every single molecule. That would be an impossible thing to deal with. So it's not totally surprising.
You couldn't windsurf on that information. Yeah.
It's not totally surprising that the better you try to do and the better the description, the more scrambled it's going to look. What's also new here is something very different than in the other situations. In the other situations, getting more and more information usually means more and more detail about smaller and smaller distances. What I think we now know is that at some point that's going to reverse itself. And what's going to happen is when you look in more and more detail, things will start to look fuzzed out over bigger and bigger distances. And so in the end, the most perfect, the most accurate description and the most scrambled description of something is going to be stretched out over the whole boundary of space. That's called the UV-IR connection. And what it means, UV stands for ultraviolet, and it really just means small distances. IR stands for infrared, and it means very big distances. And we're getting a little bit, I don't say confused, I'm not sure it's confused, but something is happening where as you start to look at a system at more and more precision, what you might have thought that you're going to see more and more tiny, short distance, small distance precision, it's going to start getting fuzzed out and fuzzed out and fuzzed out until it's stretched across the whole...
and that's not simply a feature of the camera you're using or the resolution. That is a fundamental feature of nature. That's a fundamental
aspect of physics, that the better you try to look and the more detail you try to see with, the more it's going to be stretched out and fuzzed out over bigger and bigger distances.
Yeah, I want to follow up on that. So at least one of the reasons why we're now more and more convinced that the holographic principle is really something that works comes indeed from string theory, which is my field. And what happens there is precisely if you go through this step of looking in more and more detail at what happens on shorter and shorter distances, you might be interested in say, what happens inside of our nucleus, inside of our atoms, and there's a nucleus, and there are quarks, and there are smaller and smaller particles. And suppose, again, that for a moment you would want to forget about gravity, but you start looking more carefully at what we're made of. And then because of this idea that when you start looking at smaller and smaller scales, or at least at smaller and smaller distances, suddenly you discover that there's actually something new happening. And that something new, at least in terms of your equations, you recognize it as gravity. So the amazing thing is that while you're actually interested in just looking at the smallest constituents of matter without putting gravity in, gravity comes out as something that's sort of inevitable. And to me, there's an enormously deep lesson there that gravity is something that you cannot do without. Clearly, we cannot do without it. We would not be sitting here. We would be floating in this. But,
although gravity for me and Stephen Hawking is kind of a pain in the ass sometimes, but, which is why we love to forget about it. But gravity is inevitable, but it's also a door to this something else.
It's a door to this something else, but you can get it out of something where you don't put it in. So it's not the starting point. It's the output.
All right. Well, we're gonna have to wrap this up. Let's just poll the audience. How many of you clap if you think that we are just a projection? Clap if you think that we are actually real. And clap if you don't care. You know, I would have thought that would have gotten the biggest clap of all this far downtown. First of all, I want to thank our panel. You've certainly taken us on a great journey tonight. There's obviously so much to think about. I would encourage, if you're interested in these ideas, tomorrow we're actually doing a Rebooting the Universe, another exploration of the universe as an information space at a panel here. I also encourage you on Sunday in the Kimmel space upstairs. Mary Seidman and the Keystone Dancers are going to be doing a fabulous sort of mapping of dance onto the Messier catalog and objects in the universe. So this idea of one information space mapping onto another is a theme here at the World Science Festival. I encourage you to explore all of it. Thank you so much for coming, and thanks to the panel.